we should be able to learn that you can explain different dewatering methods available, and what are different soils to which they are applicable. Okay, then you will be able to identify the types of dewatering methods appropriate for various soil conditions. So that is another objective. We need also to know that what are the common issues or problems once you start dewatering, or you want to remove the groundwater, or you want to lower the groundwater table. So what are the associated risks and problems? So, that is, you'll be able to know. And some basic requirements of the design of a dewatering system. So these are few objectives of this topic. So let's move on. The very first thing you need to know is what is dewatering. Okay. So if you look at the definition, it simply means removing or separating the water from the soil. Okay. Of course, once we say water, it means the water in the voids, which is the groundwater. So you have to separate it from the soil, or taking the water out of the particular construction problem completely. So you may remove it partially, you may remove it completely. That is called as dewatering, depending on the situation. We will see later on what are these possible situations. Okay. So what is the main objective? Of course, if you look at this figure, you need dry area to proceed with your construction, as simple as that. So if you have some excavations which are below groundwater table, so surely you need to remove the groundwater as a temporary solution or as a permanent solution, so that you can have dry working area available. Okay. So the objective of dewatering, like is mentioned over here, for construction excavations or permanent structures that are below, like I said, groundwater table, and they are not waterproof, or even if they are waterproof, but they are not designed to resist the hydrostatic pressure. So that is important. That mostly, if you are designing, for example, some light weight structures, then maybe they are not designed to resist the hydrostatic pressure. So uplifting will be an issue. So in that case, maybe you need some kind of permanent dewatering sometimes. So dewatering can be permanent, it could be temporary. So we'll see what are the differences later on. Before we move on to the dewatering methods, the most important thing you need to know is that if you do not design a dewatering system properly, then what will be the consequences? Okay, so it's important to know. The very first thing is your support systems, which you have used for excavation, maybe any type, maybe it's secant walls, it's sheet piles, it's retaining systems, whatever you have designed. So this will become unstable. Okay. Then you can have settlements due to change in soil conditions, because if you do not design the dewatering system properly, lowering the groundwater table can cause settlements to, of course, in dewatering system will of course lower the groundwater, but the point is, if it's not lowered in a way it should be, or kind of a controlled lowering, and considering the effect of this lowered groundwater table onto the existing structures, so you should expect settlements to the existing structures. Okay? Even I can say future settlements as well, because of the consolidation of the soil. You can have environmental impacts, because once you are removing water from the ground, and if that water removal is near a site where you have some contaminants already mixed into the aquifers, so with your dewatering, it's going to move into the groundwater, and then you can have environmental issues. Okay? Of course, with all these situations, you can have loss of time, and it can add to the cost of the project. So these are some important, I would say, consequences. Of course, like I mentioned over here again, work site safety. This is of course related to all these things, like if your system becomes unstable and you have some humid environment due to very high groundwater tables and they are not removed properly. So the work site safety is also an issue. Okay. So before we really move into the dewatering systems, the very first thing I want to discuss in this lecture is that to review our concepts about permeability. Okay, let's just quickly go through from the concepts of permeability. You know that maybe you are familiar with this, or even if you're not, just please I would request to go through from these topics, like how to calculate the permeability based on empirical formulas. Okay, we have a lot of formulas where you can use some basic index properties of the soil or some other physical properties of the soil. So if you already know these simple properties, sometimes even the grain size and plasticity index, these kind of properties, so you can have a fair estimate of the permeability of the soil. But you know that permeability is very sensitive property of the soil because it depends on the soil structure, it depends on the nature, the shape of the particles, and are they disturbed or undisturbed. So if a soil is disturbed, that means you have already disturbed its structure. So once the structure of the soil is disturbed, the permeability will be altogether different. So be careful in using the empirical formulas, okay? Then the next solution for getting the permeability is that you can do the tests in the lab. For sure, the most important thing in this case would be getting an undisturbed soil sample, which is not an easy job. And mind it that even if you get a very undisturbed soil sample, it is not totally undisturbed because once you get it out of the ground, that means it is under no confining stress conditions. And having no confining stress itself is a source of disturbance, which can cause kind of, you can say, swelling of the soil. And once the soil gets swelling, that means its structure, its void ratio is changed. So once the void ratio is changed, so permeability of the soil is it's going to be different. So that's why mostly we do not perform laboratory tests on the soil samples which we retrieve from the ground. Rather than that, we make reconstituted soil samples in the lab at a given density, at a given moisture, at a specific given void ratio, and then you can somehow replicate the field conditions and you can get the permeability. So, but even sometimes you can have high quality undisturbed soil samples and you can perform lab tests. Okay. So keeping in view the limitations of the lab test and the empirical formulas, the most preferable, reliable, accurate methods are the field tests, like we have borehole pecker tests, or you can do field pump tests. I'm not going to go in the details of these tests, but I would request you to please go through from the basics of the pecker tests and field tests, pumping tests to get the permeability of the soil. Okay. Yeah, if you look at the sequence, that's important that if you start with empirical formulas, so mainly for feasibility designs, that's okay. You can use. Laboratory permeability tests are mostly good for research purpose, for getting kind of a parametric studies. You want to evaluate that how different conditions will change the permeability of the soil. So in that case, option number 2 will be applicable. But if you are looking for accurate results of permeability, the most important tests are the field tests, important as well as accurate and reliable. But of course, it's going to add to the cost of the project, okay, for sure. Yeah, some basic review of the concept of permeability. You know that if you can recall the Darcy's law, the famous law for flow of water through the soils, but remember its limitations. One of the limitations is it's applicable to one-dimensional flow of the soil. So I would request again to go through from what are the basic limitations or applications of Darcy's law. But never mind, what it gives you that you can get average velocity of the flow through soil, like with this expression, which is velocity is K times I. K is the permeability, coefficient of permeability, or you call it as a hydraulic conductivity, and I is the hydraulic gradient, which is of course give head loss over a given flow path or a flow length. Okay, so but remember that this average velocity is actually based on the area of the flow, considering the area of the solids as well as the area of the voids. So that's why sometimes they call it as the apparent velocity of flow, which is not the true, or which is not the, I would say, the seepage velocity, not the actual velocity of flow. So for actual velocity of flow, you need to consider only the area of the voids, not the area of the solids. So once you consider only area of voids, this expression can be converted into actual velocity. Sometimes they call it as a Vs, seepage velocity, which is actually V over NE. Normally they write NE over here, effective porosity. Because it cannot be just porosity, because effective porosity for clays and effective porosity for sands is different. You can estimate it somehow. Okay, so V over N, and you know that porosity, the maximum value, porosity is normally represented in percentage, so maximum value of N would be 1 or 100%. So this number will always be 1 or less than 1. So that means your actual velocity, or you can call it as a seepage velocity, will always be more than the average velocity, or which you call as velocity based on the total area of flow. Okay. So this is something you need to remember, that this is the seepage velocity. So V over N, okay, where N is the porosity. Yeah, you need to calculate the quantity of flow, again by Darcy's law. You can do that, which is K times I times A, again permeability multiplied by the hydraulic gradient, and you can then multiply with the area. So this is the area I was talking about. So if this area includes the area of the solids as well as area of voids, so that's why you get the in this expression, this velocity Ki is actually the average velocity, but if you divide Ki with the N, you get the actual velocity of flow, or seepage velocity. Okay, just to recall some of the tests which you did at your undergrad level regarding permeability tests. For example, you have constant head test, you have falling head test, and if you can recall, we know that constant head test is normally done for the soils with relatively high permeability, and falling head tests are normally done on the soils with very low permeabilities like silts and clays. So in constant head test, the word itself tells you that the head has to be maintained throughout the test. You can see that you have a soil sample, it could be reconstituted, it could be undisturbed. Then you allow the water to flow through the soil for a certain period of time such that you get a steady state flow conditions. Of course, you can monitor steady state by noting down the amount of water coming out of this cylinder. If this amount of water for a certain period of time becomes constant, so you can, in simple words, you get a constant flow rate. So you will consider it as a steady state, and then you can take your readings or notes. Okay, you can see that the water will be allowed to fill on this cylinder, and then the excess water will automatically be taken away. So that means in any case, the water level in this above the soil will not exceed this point, because the excess water will always flow out, is taken out. So this head will be permanently maintained on the soil sample. So once you have this steady state conditions, so you will have Q is the volume of water for a certain period of time you are getting, the time is there. L is the height of the soil sample or length of soil sample. H is the head, which is constant. A is the area of the soil. Again, based on Darcy's formulation, this A has to be the total area of the soil. Otherwise, for seepage velocity, I told you that it has to be the area of the voids rather than the area of soil, because water is flowing through the voids, not through the whole cross section. Never mind, this is the expression which you use to get the value of K, permeability, in meters per second or feet per second, whatever system of units you're using accordingly. Okay. Similarly, falling head test is, like I said, it's for soils which have relatively low permeability. So constant head test, it's difficult to get the permeability of soil with constant head conditions. So what normally is done, that you have a soil sample and you have kind of a cylinder like this, in which you allow the water to pass through the soil for a certain period of time. And like I said, whenever you get the value of K, it is always based on steady state flow conditions. So that means you allow, first of all, you allow the water to you keep water flowing into this burette or in this pipe, and then you allow the water to go out of the soil sample. And ultimately, a stage will come that you are monitoring this flow rate and it becomes constant over a certain time period. That means you may take 2 or 3 readings and you see that the flow rate is constant, so that is steady state. So once you get steady state, then what you have to do is that you will just stop the inflow of the water from here. So as soon as you stop the water, you can see that the water supply is stopped. So, but still there's a high head over here, and water always flows from high head to low head. So it will start flowing into the soil, and it will start flowing out from here. So that means the head is going to decrease. That's why we call it as a falling head test. So as the head decreases, you have started the stopwatch at this time once you stop the flow of water. So, and then you note down the time for a certain decrease in the head. Of course, it could be any number you can pre-decide before the start of test. So once you reach up to your desired or target head decrease, so you just stop the valve or stop the stopwatch as well, note down the time. So that means you need to note down two important things from here, that for a given change for a given time, how much head decrease, or in other words, this decrease in head took how much time. So the same thing. Okay, so you record this head available. So if you see H1 is the head available at the start of the test. Okay, and H2 is the total head available at the end of the test, where you stop the test at this time. So you have H1, H2 readings, you have the length of the sample, you have the area of this tube. Okay, this is small a. You have area of the soil sample. Okay, again, it includes all the cross-section area, and you need to note down the time for which this change took place. So this formulation will give you the coefficient of permeability through falling head test. But like I said before, it's not easy to get the undisturbed soil samples. So mostly for reconstituted soil samples or for research purposes, for some parametric studies, it's good to perform these tests. But in any case, if you need a very accurate value of K, it's the most preferable method is to do the field tests. Okay, these are some ASTM standards or some guidelines I've just given to you. Please go through from them and see what are the different types of permeometers or the permeability test apparatuses which are available. Commonly, they are known as rigid wall test and flexible wall test, depending on the type of the permeometer you're using. We call this setup as a permeometer. Okay, so you can see some of the guidelines and the standards given over here. Okay. The main difference between flexible and rigid wall is that the rigid wall permeabilities, they are simple apparatuses. I'll show you some photos afterwards. But the problem is they have leakage along the side wall. So that leakage, especially it happens once you have a sample which, when it gets, it shrinks, so you get water moving at the sides of the sample. So that means you're not getting the actual permeability. So in that case, we still have some solutions like using double ring equipments. Okay, but there's a better solution is using flexible wall permeaters, because it has a membrane on side of it and there's no side leakage, so it gives you a better K value. But there's another issue that because it has different effective stress on top of the sample and at the bottom of the sample, so you have different effective stress. That means K is not same throughout, because K is highly dependent on the effective stress, because effective stress changes the structure, the void ratio of the sample. Okay. So I would request you to please go through from these standards or have a look on these kind of different types of permeometers. Like I was mentioning, rigid wall permeaters, these are all different types of rigid wall permeaters. Okay, sometimes shell by tube, sometimes compaction permeaters, just like compaction molds. Okay, sometimes they're using double ring permeaters to get the permeability in the lab, and alternate to them because they are having issues of water flowing through the sides of the sample. So to resolve this issue, the alternate is using this flexible wall. This is exactly the same as that of what you have in a triaxial cell. Okay, so but you can instead of applying the load on top of the sample, you can use this triaxial cell apparatus for measuring the permeability of the soil if you have all the mechanisms of flow lines and allowing the water to flow through the soil. Okay. So this is how you can deal with the lab tests. You can see the details in their standards. Yeah, permeability testing. Usually we test soils with very low permeability coefficient, like less than 10⁻⁹ meters per second, because above it is clay, and it's hard to test any soil with the permeability higher than that. because of it's going to take a lot of time to saturate the soil first and then perform the test under steady state conditions. So normally you are using this expression to calculate the velocity, which is Ki, like I said before. Of course, negative we use because of the hydraulic gradient I. Okay, because change in head is normally taken as negative, and negative will cancel negative. So to make the testing practical means, when I say practical, that means to make it a bit less time consuming, what you can do is you can increase the hydraulic gradient so that the velocity of flow increases, and you can get easily the test results of the lab permeability. But once you will, well, yeah, this is a guideline that how much maximum hydraulic gradient you can increase for certain K values. Or when I say certain K values, that means they are representing certain soil types, maybe starting from sand to silt to, and maybe more less than that is clay. So this is the maximum hydraulic gradients you can increase so that you can complete the test comfortably at the less time. But the problem is that once you increase I, this will cause an increase in flow, seepage velocity, and that will cause cracking in soils, and this will create an unrepresentative flow regime. That means you should not expect kind of laminar or one-dimensional flow through the soils. So in that case, the Darcy's law will no more be applicable. Okay, and also it can cause internal erosion because a very high I means high rate of flow as well, or velocity of flow, and that can cause soil particles to move with it. And similarly, it can add the leakage from the edges, from the sides in the test apparatus. So these are some limitations of doing the permeability tests in the lab, which we have to keep in view before getting to any permeability numbers. That's why we have to go for field tests. And like I said, field testing is more reliable, but at the same time, it's more costly because uh, you have to make boreholes into the ground, and these holes then will be pumped. So you have to install the pumps. You have to have some wells or some boreholes near this pumping well, or we call it as a pump well or test well, and like it's mentioned over here. Okay, and the others are called as observation wells, where you are taking the readings of the level of water. So if you see over here, this is the original water level, and then you have this test well or pump well where you will pump out the water at a certain flow rate. Okay, and then you have two observation wells or boreholes, uh, kind of episometers, I would say, at a distance R2 and R1 from the center of this pumping well. Okay, uh, so and once you start pumping water, that means the phoretic surface, the original phoretic surface before pumping will go down, or as a drawdown. Okay, and this drawdown, you can see it over here, or in simple words, the level of the phoretic surface from this impermeable layer, we can call it as an H at any given location R. Okay, so this means uh, your objective in this test is to note down that for at a given distance how much the drawdown happens. So this distance will be drawdown. Okay, this is drawdown. So you can clearly see that the drawdown over here is maximum because you are pumping water from this well, and then the drawdown as you move away from the pumping well is decreasing, and ultimately it joins the original ground surface. So in these tests, you are also looking for we call it as the range of influence, that once you're pumping water and the water table is lowering down, so from the center, how much maximum distance will be affected or influenced for where you have some drawdown. So that in simple words, where drawdown becomes zero, so from that point to the center of the well, it's called as the zone of influence or range of influence sometimes. Okay, so these are some observations, values you have to record during the pumping test. Okay, and using some formulations like in this situation, we call it as an unconfined aquifer system, because you have the upper surface of the water table is exposed to the atmospheric pressure, and you have an impermeable or an equiclude, I can say, at the bottom. So this will give you a permeability with this relationship where Q is the steady state flow, pumping rate, R1, R2 are the distances of the observation wells from the center, and H1, H2 are the respective heads at these two observation wells, or you can call it as a piezometers. Okay. So once you have these numbers with you, you can get the value of K permeability. And this is going to be quite a reliable number because it's for in situ conditions of the soil. Okay, these are just some typical cross sections of observation wells. I'll not go in that details, but this is how they're constructed actually. What type of situations or you have to do, the treatments you have to do in these observational piezometers. Like you can see over here, this is a typical figure once you have only a small test section. Means you are expecting the drawdown only in this range. So this is going to be your plug. We call it as a plug where the water table will be rising or falling. So you will record your the values accordingly. But sometimes you have very thick kind of aquifer. This is an aquifer, which is a saturated zone of the soil. Okay, you can see this is representing the test section from here to here. So you have a very thick deposit of aquifer. So this your test section would look like this, or in simple words, the observation well will look like this. And if you have stratified soils, like you can see again over here, you can see sand or gravel backfill over here, but that is just for purpose, so to allow the water to come into the test section so that you can note down these readings. So these are some construction details actually. Let's mention over here, specific zone, and it is the entire borehole. So depending on the ground conditions. Okay. Again, the test is quite expensive. It needs time and it needs expertise as well to analyze the data, because I'm just showing you one possible condition over here where you have an unconfined aquifer. The aquifer is exposed to the atmospheric pressure with impermeable layer on the bottom. But there are many possible situations with stratifications, with confined aquifers, and some other possibilities. So the formulation and accordingly the calculations for K would change. Okay, so you have to be very careful with the ground conditions. This is another formulation given by Duport theme approximation for single well. Okay, again it's a pumping test where you are pumping water from the well, but in this case you don't have an observation wells. Like in this case, you see that you need at least 2 observation wells so that you can make your calculations. Okay, for K. So in this case, you can make calculations even with one single well, which is the pumping well itself. Okay. Again, the situation I have shown is for unconfined aquifer. You can see that the ferritic line before and ferritic line after. So here are some terminologies. H is the distance from the permeable impermeable layer. Once I say impermeable layer, means this is a layer in which you can have a very low K, or I would say no K situation. No flow of water is possible from this layer. Okay, so this is going to be the high, simply a distance from the impermeable layer to the groundwater table. Then you have H naught, which is the level of the water in the well just before pumping. HS is, if you see over here, it is the height of free discharge surface. Okay, that means it has been observed that once you have a situation like this where you have a pump single well being pumped, so it's not like this that the ferritic line just meets exactly the level of the water in the well. So there is always a free discharge surface, means it's kind of it starts as a gravity flow over here. Okay, so this small area will be represented as a free discharge surface HS. So HS H naught is the level of the water just before the start of the pumping. R naught is the radius of the well, pump well, and R. If I come to this side of the figure, this R, now R, Y, S, and these are some general terms now. Means at any given distance R, so you can get the height of the ferritic surface, the distance of the ferritic. Because you see the max. If I ask you what's the value of what's the maximum value of Y, so it would be H. Okay, and the minimum value of Y just before the start of the test, it would be H naught. Okay, so that's how this Y is a variable actually. That's why you see 2 more variables over here. There is HW. HW is actually a constant which you can get it from here. It's H naught plus HS, if you see it over here. Okay, which is the initial water level plus the free discharge surface. S can be obtained accordingly if you know these numbers. So, but Y is variable depending on where is R. So, if I talk about R equals to R naught, then Y would be equal to HW. Is that right? okay, which is actually H naught plus HS. And if R is equal to, for example, more than the zone of range of influence, so then Y would be equal to H. Okay, so this is how these variables are changing. So once you have these variables with you, you can use these formulations to get the value of Q, or indirectly, if you have Q with you, the flow rate, you can get the value of K from here. So you can say this. You can get flow rate, or you can get, in other words, you can get K from here in this expression. So all the variables should be determined from the field test itself. And this is the relationship between these variables Y and HW. So you can use that to get any value of this level of the ferritic surface from impermeable layer. Yeah, this is a formulation given by Ongos to get the value of the free discharge surface, which is actually a function of H, which is, I'll show you back again, capital H. Yeah, this is the distance from the impermeable layer to the groundwater table. H naught is the just level of the water in the well just before pumping. Okay, and you can see there is a constant C, and that value is normally given fixed as 0.5. You can use this chart as well. The reference is given. You can see more details where you can get the value of, yeah, this is the R I was talking about. So you can see from the pumping well, let's assume there's the pumping well over here. Okay, so the drawdown is there. So you have a maximum drawdown over here. As you are moving away from the pumping well, the drawdown is decreasing, and ultimately it becomes 0. So where the drawdown becomes 0, in simple words, the ferritic line before and after becomes the same. So at that distance is referred to as R. Okay, and R is called as influence range R. Okay, so that means R is going to be a constant depending on the conditions, soil conditions, and the flow, the pumping rate, and all these things. So this is to be calculated. H is to be determined accordingly. Of course, H is already known from the topography, from the underground, from the subsurface information available to you from the borehole logs. Okay, so what you are looking for is HS and H naught during the test, and so you can proceed with your formulations. And you can see over here, either you know the radius of influence, the influence range, or radius of influence, sometimes they call it as. So you can get from here the value of HS, or vice versa, you know the value of the HS, which is the free discharge surface, and because H is constant, okay, H naught is known to you from the field test, so you can get the zone of influence, the influence range. So it's two-way chart. You can use it any way you want. So for R, we can use this formulation where C is again a constant. I'm sorry, it should be C. It's C actually. There's no need to C dash, just to differentiate from this C and this C. Maybe we put over here as a hyphen. Okay, sorry, as a dash. Okay, so H minus HW under root K. So if you have the values of, yeah, this is quite interesting over here, that you are looking for permeability of the soil through the test, and you already need the permeability value over here. So this is kind of, I'll show you with the other example later on, that how would you use this numbers. Okay. So C is a constant given for wells, 3000, and this range for single line well points means you have a lot of wells in a single line. You will use the value as 1500 to 2000. If you have single wells, normally we use the value of 3000. Okay, H is clear from here. HW is you can see it from the previous figure. What is HW? Okay, so this is H naught plus HS, which is the initial water level plus the free discharge surface. Okay. So you have H minus HW, C is a constant, K should be given or known in meters per second, okay, and you can get the value of the influence range. But in simple words, the distance where I would say this drawdown becomes 0. Okay. So sometimes you have a situation where you don't have like the pumping wells and the observation wells placed exactly like on the right and the left, like I show it over here, they can be sometimes a different arrangement. So this is point P. Point P over here means the pumping well. So you are pumping from here, and you have installed the observation well. So this well 1, well 2, well 3, they are representing observation wells. Okay, you will see in literature normally sometimes they are writing the word OW. So OW goes for observation well, and they write over here PW, pumping well. Okay, so in this situation, and of course you already know their positions, that where you have installed these piezometers or observation wells. So you know their distances x1, x2, x3. You have the pumping well. So using this relationship, you can again calculate the flow. Okay. Actually, it's a two-way relationship. If you already know the flow because you are pumping out the water, so flow is normally with you. So Q is with you, and you can indirectly get the value of K. Okay. So, or you have the K, you can get the approximate flow to the well, because two-way process. Sometimes you need to know that how much water will come into your excavation. Okay. So in that case, you already know the values of K, and these are numbers, so you need to know that how much water will come to your excavation, so you can use this formulation. Or other way around, you're pumping water out, you know the zone of influence range, you know the positions of the wells, so you need to know from that pumping test the K value of the soil, so you can use this expression, vice versa. Uh, Similarly, if you have an arrangement of wells in a circular way, so in this case, what you have to do is, yeah, of course, you can see that the pump. This point, red point, is representing a pumping well. Okay, so you have the radial arrangement, circular arrangement of the wells. Okay, and this is A is the radius of this circle. So R is the influence zone, and these are the same terminologies as before. You can get, again, like I said, either Q from this pumping system, or you already know how much water you're pumping out, the steady state conditions Q at any flow rate. So, and then you can get the value of K from this expression. I'll show you some examples, don't worry about that. So you'll see how to use these expressions later on. Yeah, like I was saying that sometimes it's important to know that you are making an excavation and how much water will flow into your excavation. So if you see, this is representing an excavation, and of course you can see that the excavation is below the groundwater table. So this is the initial groundwater table, or the phonetic line. And you can see this is R. Why is it R? Because from the, yeah, like what I was saying, if this is an excavation, you can even still represent it as a well. Okay, remember that. So this is going to be from the center to where the drawdown becomes 0. That's going to be R. H, you have the H naught, the initial position, and then if the water starts flowing into it, you can get this distance as H minus H naught. R naught is the radius of the well, or you can say the distance from the center to the edge of the well. It's representing as a analogy for the well. Okay? So you can use this expression by Darcy to calculate the flow into this excavation. Okay, flow rate. You can see all the numbers. They will be either given or you can calculate. Okay. You can use a single well formula. It's another one. Okay. Of course, given by the same author as mentioned over here. You can see this article. Slightly different formulation, but the concept is almost the same. Okay, so the figure is exactly the same. You can see that. Okay, the only difference is in the formulation process, considering this as a single well or considering this as an excavation using Darcy's law. So, and you will see that there's not a big difference between the answers we are getting. Okay. So you have this formulation where you need H, you need the H naught initial position, and then you need the radius of influence, zone of influence, and you need the radius of the well itself. Like I said, it can be a well, it could be an excavation, but you can represent it as the same thing. You have another option to calculate the flow rate, to estimate the flow rate, and you know that is called as flow nets. You can draw a flow net. What is a flow net? You are already familiar with this, that it's a combination of lines, and of course 2 types of lines. One is called as equipotential lines, means the lines where the total head is it's constant. So if you talk about this line, this line, this line, so every line is having a constant head. But of course, as you are moving towards the flow, the head is changing. Okay, so it's not constant. So every line has, and the difference between the two equipotential lines will give you the head loss between this distance. And this is one flow line, this is another flow line, this is another flow line. So actually the zone, the area between two flow lines is called as a flow channel or a flow tube. So in this figure you can see we have one, two, three flow lines and two flow channels or flow tubes. And if you count the number of head drops, so we can start from here. This is the first drop, second drop, third drop, fourth, fifth, sixth, and seventh. So you have 7 number of drops. So what you need is the number of flow channels. You can see it over here. For example, in this case, there are 2, and you need the number of head drops. I'm not saying number of equipotential lines because this is the first equipotential line, but the drop over here will not start. As soon as the water starts flowing, the energy is lost, and you will have a head loss. So then you should call it as a number of head loss or a head drop. So in simple words, if you have, like, for example, 10 equipotential lines, so you will have 9 equipotential drops. And if you have 3 equipotential lines, flow lines, you will have 2 flow tubes or flow channels. So always one less than the number of lines, whichever you're talking about, flow lines or equipotential lines. So once you have drawn this flow net either manually or using some tools, like you can do it in CW, it can draw flow nets for you, okay, in GeoStudio program. And once you get the flow net, you can calculate the flow rate by using this expression. Okay. And there is another estimation formulation available for rate of flow into a pump well or a well point. Okay. So this is given by Bosch in 1971. This relationship can be used. But be careful, guys, that these all equations have their own system of units. So you have to use the respective units. So K is the permeability in this expression, and feet per minute. Okay, be careful with this. But mostly you're getting your answers in feet per second, so you don't use it in feet per second. It has to be feet per minute. RW is the effective radius of the well. Like I'm using the word effective radius of the well because you can convert a multiple well point systems. Maybe they are square or rectangular in their patterns. You can convert that into an equivalent circle, and you can get an effective radius of the well from that conversion. And H naught is the depth of the immersion of well. Means like I said before, the level of the water just before the start of the pumping. Okay. So again, like I said before, don't worry, we have an example to explain all these equations, the use of all these equations. Before I move into those discussions where we'll solve an example, guys, remember that whenever you are doing a dewatering or removal of the groundwater, so it's very, very important to make sure that the bottom of the excavation remains stable. Why is that a concern? Because if you see the situation over here, so you have somewhere here the original water level, and then you start using any type of systems. We haven't discussed so far these type of dewatering systems. Don't worry with that. This is our next discussion. So, but the objective of any system is to bring the water table or the down or below the excavation. So now you have an excavation in dry, but remember, still you have sometimes situation like this. If you see over here, it's a sand layer, it's an aquifer, but now this is confined between two clays, so it's going to be a confined aquifer. That means it will be a pressurized flow. So once you have a pressurized flow, that means you have a very high uplift pressures or artesian pressure, we call it, as available at the bottom of the foundation, at the bottom of the excavation. So if this pressure exceeds the overall stress above at this point, so that means you will have a chance of sand boiling, or they call it as heaving. So again, I would request you guys to read what is sand boiling, what is ground heaving, under this situation. So you can get more details. Simply the rule is that this gamma times z, which is z is this distance, if you see it over here, because this is an artesian well, or I can say a confined aquifer. So gamma into z should be more than gamma of water into h plus z. So h plus z, if you see h plus z is the distance from the original groundwater table to this level. So this is kind of, you can say that before an excavation, this is available, I would say, stress at this level, and this is the stress once after the excavation. So it should be more than that. If it is not, like I said, it's going to be a ground heaving problems or sand boil problems. Okay. Uh, Another thing you should remember to keep in your design, that your adjacent structures, nearby structures, they will surely settle down once you are pumping the groundwater table. Because if you have, for example, a structure over here nearby this excavation, so your initial water table is here, final water table is here, that means you created a change in water level. Okay, and that delta H, which is the reduction of water level, times gamma W is actually the induced stress. It's the extra stress, change in stress. So, and if you recall this expression of calculating the, the one-dimensional consolidation settlement through Tirzavi's theory, so if you can recall this expression, that you can see that any change in stress will generate a settlement, consolidation settlement in the soil. So if you have nearby structures, and if you're lowering the groundwater table and you're creating a big difference in the original and the final water table, that means you are creating a big change in the effective stress. And a change in effective stress will ultimately lead to the settlements. So this is very carefully, you have to consider this in your designs. Yeah, okay, I think I can give a pause here. So in part two of my lecture, I'll be moving to dewatering methods in more details. So this was all about like just refreshing our knowledge on permeability, different types of methods available. So I would just like request you to please go through in detail of these discussions, which I've just explained to you now. Uh, Read something about the lab permeability tests, especially I haven't mentioned any relationships, empirical correlations for permeability. I would request you to look for these relationships and list it down, share it with your fellows, with your colleagues, and even share it with me so that we can see what are different relationships available for calculating the value of permeability based on some other physical or index properties of the soils. Okay. So this is part one. Uh, I'll be moving to part two in my next lecture, inshallah. So let's have a stop.